Good evening, one and all. I am happy to welcome you all to this session. And let me introduce our speaker of the session, Dr. Sreelal S, sir. He is currently the chair of Circuits and Systems Society Kerala chapter and a senior scientist at Vikram Sarabhai Space Center, ISRO, Trivandrum. And on behalf of all of you present here, I cordially invite Dr. Sreelal S, sir, to deliver the talk. Dr. Sreelal S, sir.
Thank you, sir, for that introduction. So we will start off. I will try to share the screen. Is my screen visible?
Yes, sir. Yes, sir.
It is visible, right, sir? As a slide.
Yeah, it's visible, sir.
Yeah, it is visible.
Yeah. Thank you. So today's topic is low power smart electronics, mainly for Internet of Things and also for aerospace applications. So the basic outline of the talk is I will start off with an introduction, then what is the need for low power IC design and what are the techniques for low power IC design, then low power system design. How is the system design aspect tackled for low power? The hardware aspects as well as some software related aspects we will touch upon. Now, this is not meant to be an exclusive coverage on the low power design techniques, but basically we will be touching on the key points. That is what is meant here. And then we will see some case studies with a specific example of a wireless instrumentation system in detail that we have used in our applications back in ISRO. And then some of the Internet of Things applications also. And finally, I will conclude the talk. So the importance of low power design, that is the first topic that we have to deal with. Power is considered as the most important constraint in embedded systems. We all know that power is a very key factor in the design of embedded systems. Now, low power design is essential for high performance systems. The reason is that excessive power dissipation reduces reliability and increases the cost imposed by cooling systems and packaging. And also it is important for portable systems. The reason is that battery technology cannot keep pace with demands for light batteries and long time between recharges. So it is also important in the context of what we do back in ISRO, that is avionics for long duration missions, especially for missions like interplanetary missions, Mars missions, etc., where the duration goes to months or even years. It is very important that the electronics takes as much less power as possible, because that will help you to optimize on the battery that is used for the payload. Now, what are the power and energy of circuits? The power and energy are related by, as we all know, E is equal to integral of P dt. That is, energy is basically the integral of power. So minimizing the power consumption is important for the design of the power supply, the design of voltage regulators, the dimensioning of the interconnect in the ICs as well as on the board, and then for short-term cooling. Similarly, the minimization of energy consumption is important due to restricted availability of energy in mobile systems. As we all know, our mobile phones, for example, are working on the lithium-ion battery, and the weight of the battery depends upon, and the number of times we have to recharge it depends upon how much power the electronics inside is taking. So limited battery capacities and very high costs of energy also are important, especially in space. For example, we harvest energy, as you may all know, from solar panels, and therefore there is a limitation in the amount of energy available, and that too when the satellite is facing the sun only it can be done. So cooling is another aspect which involves high cost, limited space, long lifetimes, and low temperatures. So low power can be achieved at various levels of design. For example, at the top level, at the system level, we do it by doing appropriate design partitioning and appropriate power down methods of design. Then at algorithm level, we do it by reducing the complexity, then by introducing concepts such as concurrency, locality, regularity, etc. Then at architecture level, we can adopt techniques such as voltage scaling, parallelism, instruction set, signal correlations, etc. At the circuit level, we can do transistor sizing, logic optimization, activity-driven power down, low swing logic, etc. And then at the process and device level, by suitably reducing the threshold voltage of transistors and by using multi-threshold in your circuit. So this is basically the entire hierarchy of the IC design as well as the system design that we are dealing with here, with the process and device level at the bottom and the system level at the top. So this basically shows how a low power can be achieved at these various levels of system design. So the design of low power circuits can be tackled at different levels from system to technology. That is the basic message from this slide. So at OS level, we are having techniques such as partitioning, power down, etc. At software level, we are having techniques such as regularity, locality, concurrency, etc. At architecture level, pipelining, redundancy, data encoding, etc. help us to minimize power. Then at the circuit and logic level, logic styles, transistor sizing, energy recovery, etc. And at the technology level, as we have seen, reduction in threshold voltage, multi-threshold devices, etc. help us to optimize the power. Now let us see the major techniques that are that we can adopt in for the low power IC design. So this is basically the diagram of a CMOS logic or inverter. Now in this, we all know that there is no static leakage. That is when either 1 or 0 input is present. That is when a static input is present, one of the transistors will be off, and therefore we know that there is no static power consumption for this. So what is the dynamic power consumption? So basically the power consumption in CMOS comes when switching activity takes place. That is called the dynamic power consumption, and it occurs due to charging and discharging of capacitors. It occurs due to short circuit currents, that is a short circuit path between supply rails during switching, and it also occurs due to leakage of diodes and transistors. So these are the three sources for power dissipation in CMOS. So the power of a CMOS gate during transition is given by the dynamic power equation CL VDD square F plus PSC. The static power is given by VDD into I leakage, where VDD, as we all know, is supply voltage. CL is the load capacitance that the inverter sees. F is the switching frequency. So this is basically the dynamic power and the static power equations of a CMOS gate. Now the power consumption of VLSI chips, why should we be concerned about that? That is one of the major questions that we have to answer. Now, this is basically taken from the International Solid-State Circuits Conference keynote, which was given by Mr. Patrick Gelsinger, who is Senior Vice President in Intel Corporation. So this was basically back in 2001, but the basic the principles behind the need for power reduction can be seen from this. 10 years from now, microprocessors will run at 10 gigahertz to 30 gigahertz and be capable of processing 1 trillion operations per second, about the same number of calculations that the world's fastest supercomputer can perform now. Fortunately, if nothing changes, these chips will produce as much heat for the proportional size as a nuclear reactor. So this is basically where he predicts that the chips will be capable of very fast operation, but at the same time, we have to be concerned about the power consumption because they are going to dissipate power similar to that of a nuclear reactor. So this is another graphic which illustrates how the power density, that is in watts per centimeter square, has been going on increasing as the various generations of IC technology have been introduced. Now, earlier, from very early times of 1970s, where devices such as 8008, 8080 microprocessors were used, to the present new generation of Intel processors, we can see how the power dissipation, our power density has been rising. Around 2000, around the year 2000, it equaled that of a hot plate. Around the year 2005, it is quite similar to that of a nuclear reactor, and around 2010 or nearing 2010, it became quite close to that of a rocket nozzle. And soon we will go to power densities that are very similar to that on the sun's surface, but unless we do something about this. So this is basically a graphic which illustrates the severity of the problem of power dissipation as the IC technology scales. Now, this is basically another graphic which illustrates how the voltages, supply voltages and the currents have been scaling with the various IC technologies. The voltages, as we all know, have been coming down as the new generation technologies have been introduced. But at the same time, the currents have been keep going on increasing, and therefore the power per chip in watts, which is shown by the blue line, is also going on increasing, or it is quite on the increasing trend. So this is again another graphic which shows the need for reduction in power consumption. So design practices that reduce power consumption by at least one order of magnitude is very desirable. Now, these low power design methods can be tackled, as we have seen, by algorithms and architectures, high level and software techniques, gate and circuit level methods, and by testing for power. So the dynamic power consumption, again, if you revisit, the quantitative formulation is CL into VDD square into F 0 to 1. That is the frequency at which the transition from 0 to 1 occurs, which is again CL into VDD square into P 0 to 1 into F, which is basically the frequency at which the 0 to 1 transition occurs, which can be written as C effective into VDD square into F. So power dissipation is data dependent function of switching activity. C effective is some sort of effective capacitance which is given by CL into probability of 0 to 1 transition. P actually indicates the probability of 0 to 1 transition, and F indicates the clock frequency in this equation. So the research efforts in reduction or in reduction of power consumption or in attaining low power design can be classified into reduction of the active load. That is basically reduction of the capacitance factor CL. This can be done by minimizing the circuits, use more efficient design, charge recycling, more efficient layout, etc. Then a reduction in supply voltage VCC can be achieved by technology scaling, which is the highest win. Thresholds should also scale appropriately. Leakage is another factor which starts to set in as we reduce the supply voltage and the technology and advance the technology. Then dynamic voltage scaling is another step which can be used. Then FCLK, basically the clock frequency, that is run the chips at a lower pace, use parallelism, use pipeline stages, use double-edged flip-flop. That is basically to reduce FCLK. And to reduce the factor K, that is basically the reduction of switching activity factor, we can use conditional clock. So what do you mean by conditional clock? That is when the clock is required, only we clock the chip. Then conditional pre-charge, switching off of inactive blocks. That is when a block is inactive, we can switch off that block, and then conditional execution. These are some of the techniques which can be adopted in order to achieve low power dissipation. So at register transfer and logic level, the low power techniques at RTL and logic level can be subdivided into techniques for lowering the capacitance, minimizing global communication, logic optimization by synthesis tools, and techniques to reduce the toggle rate of nodes with high relative capacitance. These are called guarding techniques, pipelining, reorganization of logic gates, operators, etc. So reducing switching activity, one of the factors which we mentioned, how do we reduce the switching activity? Basically, it can be done by guarding technique called clock gating. Clock gating basically means to shut down the clocking for certain group of registers under a certain guard condition. That is, when a particular guard condition is activated, we can shut down a group of registers. They need not be clocked. Advantages, they are implemented with minor overhead in area and design effort, and disadvantage is the testability. That is, how do we test it? Then again, pipelining is another technique which can be employed to reduce the switching activity. It can reduce the critical path, that is enabled savings due to voltage scaling, etc. It can reduce glitches. Glitches is one thing which can lead to a lot of power dissipation, because glitches basically happen due to dynamic switching activity, and they can lead to unnecessary power consumption. Then disadvantages are area overhead is more in the case of pipelining. Then reorganization of logic gates and operators is another method. That is, manual reorganization is possible. Automatic reorganization, which can be performed by synthesis tools, is possible. So these are various techniques which can be again employed with the aid of tools also in order to reduce the switching activity. These are two examples of reducing switching activity. For example, the full adder circuit as given on the left side can be implemented by using the circuit on the bottom, which basically reduces the number of levels. As you can see, at the top we are having 3 levels, whereas at the bottom we are having only 2 levels, which will help to reduce the power consumption. Similarly, the right side shows a logic diagram where we are having 3 logic gate levels, which can be reduced to 2 logic gate levels in order to reduce the power consumption. So these are examples of reorganizing the logic in order to reduce the power consumption. Similarly, in sequential logic optimization can be performed by state encoding, by suitable encoding of states, data encoding and data pass, then retiming for low power. So these are some of the techniques which are used for reducing the power consumption by sequential logic optimization. At the physical level, at this level of abstraction, the number of manually guided optimizations is quite limited. The place and route tools automatically minimize the wire length and wire capacitance, but this doesn't represent the optimum for power consumption. There are some design tasks which can nevertheless be exploited to save power. For example, partitioning properly and then back annotating and doing the simulation. So these will help us to optimize the power consumption at a physical level. Now, that is basically all about some of the key points. Again, I want to reiterate that we are not giving an exclusive coverage of the low power design techniques here. Some of the techniques we have touched upon. Now let us see the low power system design aspects. So basically, in the case of low power system design, we are having various silicon choices. The leakage current is the dominant source of power consumption in CMOS. It worsens with scaling. That is one of the things. For example, in our mobile phones itself, if you see, our mobile phone may be in standby mode for quite a long time. For example, let us assume that we are operating the mobile phone in the morning and then till evening it is in standby mode. So it basically doesn't do any activity. But if we turn on the mobile phone in the evening, we can see that there is some battery charge which has drained away. So why does it happen? That is basically due to the leakage current of the circuit inside the mobile phone, which happens even if the mobile phone is in a standby mode. So as we have seen in the case of inverter also, that 2 transistor inverter, even though there is no static path for the current, we can see that there will be a small leakage current flowing from the power supply, and that will lead to the battery drain. So circuit techniques to reduce leakage are clock gating and power gating. It can be done by using appropriate process technology, that is application of a duty cycle for active power and standby power, then clock distribution, appropriate clock distribution, voltage scaling, and then by proper power distribution on the system as well as the chip. So here is the leakage factors. The subthreshold current is the dominant factor in this for leakage. So if we consider this inverter, we can see that the subthreshold current of the bottom transistor is one of the dominant factors which lead to the leakage current. So what is the subthreshold current? We can see that this is the characteristics of a MOSFET, where the drain current is plotted on the y-axis, the root of drain current in fact, versus the gate to source voltage on the x-axis. Here we can see that the transistor turns on when the gate voltage becomes equal to VT. So as we reduce the transistor threshold voltage by scaling, we can see that the current at is equal to 0, that is basically the y-intercept of the curve that we can see here, also goes on increasing. So that will lead to a static power dissipation. So that is the basic subthreshold current that we are talking about. So performance scaling, dynamic voltage scaling, control the active to sleep duration ratio, and memory usage. These are some of the techniques in order to reduce the power consumption. Then code optimization, then optimize the code properly, and tools for energy efficiency. There are several tools which aid us in reducing the energy. That is a linker that understands, for example, the memory map of the microcontroller, and tools that can examine the organization of peripherals on on-chip buses. These are some examples of tools that can help us in reducing the power consumption. Now, given a certain application, there are several possibilities for low power. Selection of an optimum algorithm, partitioning into building blocks, voltage frequency scaling, dynamic power management, then minimize waste and overhead. These are some of the techniques. So we can look in detail into each of these, but we will just go into it in a brief manner. Algorithm selection and optimization is one thing. For example, power reduction is possible by scheduling of operations and then adaptive implementation of certain algorithms, what you can see at the bottom. So that is, for example, two algorithmic techniques which can help us to reduce the power consumption. Then optimization of memory access is another thing. As we all know, when a chip has to access memory, then a lot of power goes for that. So optimization of memory access, avoid using memory operands as far as possible, then improve register utilization. Then because if we improve the register utilization, then the memory will not be accessed. Then 15% reduction in time can be obtained by hand tuning the performance. So 5% reduction in current, 7% reduction in time, etc. Further optimization can lead to further reduction. So totally something like what they have calculated is by optimizing the memory access, approximately 40.6% of reduction is possible. Then design partitioning in a proper way. Optimum partitioning of the design will result in orders of magnitude power reduction. That is another method in order to achieve power reduction. For example, hardware software partitioning, that is which task will be carried out in hardware and which task can be carried out in software. So then again, optimum partition of a design into analog and digital sections. These are all possible. These are all feasible techniques to reduce the power consumption. Then design partitioning, which leads to interconnections. Interconnect power is important. Interconnect may contribute large percentage of power. So the interconnect power is greatly affected by the architectural level decisions. So common design approaches are a processor usage model where system is idle and then background process. So compute as early as possible. Clock frequency reduction, voltage scaling. These are some of the techniques which we have already seen. So this is basically the as early as possible computation technique. We will not go into the details of this. Then clock frequency reduction, that is another technique which can be used, which helps to reduce the power dissipation. Then voltage scaling, that is reduce the voltage properly. And nowadays, even there are circuits which scale their own voltages according to the activity that is required. That is by sensing the activity that is required, the appropriate portions of circuit can be operated at a lower voltage. Or if you want only a lower performance, then it is possible to operate at a lower voltage. So with voltage scaling, we reduce the VDD, but the delay of circuits will increase, but at the same time, their power consumption will reduce. So whenever you don't need very high performance, it is possible to reduce the voltage and then save on power. So again, voltage scaling can be applied at architecture level, circuit level. These are various levels. Then dynamic power management is a design methodology that dynamically reconfigures the electronic system to provide the requested services with the minimum power consumption. So that is those are techniques that are possible at the system level. Now let us come to some aspects of what is called green electronics. So what do we mean by green electronics? It is basically environmentally friendly or environmentally sustainable electronics. It can be biodegradable, biocompatible electronics. It leads to decreased e-waste in landfills. It leads to recycling of components. It leads to non-hazardous operation and disposal. It also leads to lower energy use per carbon emissions. Now, this is very important in the context of the greenhouse effect, etc. So there is something called a Green Electronics Council, which assesses the global rating for the electronic systems. So there is something called Greenpeace ranking system also, which provides a guide to the greener electronics. So basically, this is a movement which is used in order to ensure low energy use and therefore low carbon emissions for the electronics. So this is basically a news which came in NASA Tech Briefs. That is basically an engineer creates an origami battery. So what is basically this? It is basically a battery which has been which can be folded into the size of a matchbox, and it uses an inexpensive method with the origami paper-based biosensor. So basically, this is a typical example of a green technology that has been developed. So now we come to what is called smart electronics. So smart electronics is basically something which integrates sensors with data acquisition. So these, whatever I'm telling now, are examples of smart electronics. So integrated sensors with data acquisition, processing, and communication interface inbuilt. Then adaptive systems, like for example, signal conditioning, sampling, compress sensing, etc., in adaptive manner. Then artificial intelligence techniques for integrated health management. Then reconfigurable hardware or software. These are all some of the new paradigms. These four titles which I have touched upon now are some of the four paradigms which can be termed collectively as smart electronics. So we will see some examples of each of these. So bio-inspired computing, what is the meaning of that? Stanford engineers built a nanoscale device for brain-inspired computing. Researchers at Stanford School of Engineering have delivered a nanoelectronics synapse that might drive a new class of microchips. So basically, this might one day lead to real-time brain simulators that enhance our understanding of neuroscience and portable, energy-efficient, adaptable, and interactive computer systems. So basically, this is something which derives inspiration from our brain. So our brain is one of the wonders of nature, we can tell, because it takes today's state-of-the-art supercomputer 8.5 minutes to simulate just 5 seconds of normal human brain activity. So look at that, just 5 seconds of human brain activity. If a supercomputer is trying to simulate, it takes 8.5 minutes. Meanwhile, that supercomputer will consume 140,000 times as much electricity as the brain. So 1.4 million watts to be exact. So what we can see is that for sheer processing power, the human brain is incomparable. So that is why one of the 14 grand challenges of engineering, which has been set forth by the National Academy of Engineering in USA, is to reverse engineer the brain. That is, how do we build electronic circuits that can mimic the activity of the brain? So it is basically an intersection of engineering and neuroscience that promises great advances in healthcare, manufacturing, and communication. So basic message here is that if we are able to emulate the way in which our brain does the computation, then we can come up with very low power electronics and which is high performance at the same time. So that is the basic message which comes out of this. Now let us look at some of nature's other creations also. For example, this mosquito that we can see in the figure here, it involves a combination of bio and semiconductor. So what all does a mosquito have? It has got sensors on its head which can sense infrared, humidity, CO2, etc. It has got a very tiny brain which can do real-time image processing, artificial intelligence, 3D flight control, etc. in our parlance, if we tell it. Then it has got ultra small volume, a very small number of neuron cells, and it is extremely low power. We can just think how much power or energy a mosquito has. So basically, can we come up with some electronics which is similar to this, at least by the year 2025? That is one of the questions that possibly nature is asking us. So if we are able to do that, then we can come up with something called a biocomputer, which is capable of emulating our human brain also. So this is basically shows that the nature has got very wonderful methods of doing computation. So this is another paradigm called digitally assisted analog. So that is another paradigm in the new designs. So basic problem is that today's integrated chips need analog, and 50% of chips need analog, but only 2% of the transistors are analog. So the analog design is getting harder and harder. So how do we use digital in order to help us in this scenario? So why are we moving this way? Because the digital power scales better than analog. That is why we are trying to see whether some of the analog functions can be assisted by using digital. So it basically involves rethinking the analog design. That is when we go for a mixed signal design, we can rethink the analog design. So see the slide on the right hand side bottom, digital nonlinearity compensation. For example, if a system is nonlinear, it is possible to think about a digital compensation, a digital scheme of doing a compensation of the nonlinearity. So this is basically one concept which has been used very recently quite a lot. For example, we all know that analog to digital converters are there, which do a conversion of analog voltage to digital. Now, if we use a coarse analog to digital converter, which is named as a slopy ADC on the figure on the right hand side, and then do a digital post-processing on the digital data, then we can obtain very high precision and accuracy by suitable techniques. So that is basically the idea behind the digitally assisted analog. So this way we will be able to relax the analog precision also, or relax the demands on the analog circuitry and move some of this onto some of the functions onto the digital circuitry, which can easily scale according to the technology. So another paradigm is automated data acquisition techniques for a monitoring system. So we will not go into the details of this. This is basically used for many very different kinds of applications. Even in our aerospace application also, we do something called health monitoring, which can use this. So it uses automated data acquisition for prognosis and diagnostics of the system. Now we come to some actual case study examples. This is a MEMS pressure sensor which we use back in ISRO. What does the pressure sensor do? It converts pressure to appropriate voltage. It has got a pressure range of 0 to 1 bar, a proof pressure of 2 bar, basically an output span of 4 plus or minus 0.10 offset. So basically what we have to see here is that it is a pressure sensor, a MEMS pressure sensor along with electronics integrated into a small capsule, as we can see here. So this is basically a sensor and an electronics integrated together. So the advantage of using such techniques or technologies is that batch fabrication can be used similar to that of ICs, which will help us to reduce the cost. So design of small geometries, precise dimensional control, design flexibility, the possibility of interfacing with control electronics, then repeatability, reliability, and high yield process, low power, low cost due to mass production. These are some of the advantages which we derive when we use this. So miniaturization basically makes engineering sense, as we all know. Small systems have low mechanical inertia, they have low mass, they have minute sizes, they have got low thermal expansion, they have got less space requirements, less material requirements, and they are amenable to production in batches. So these are some of the advantages that we get when we go for miniaturized realization. So this is quite another example of a smart pressure sensor, which is a MEMS sensor integrated along with intelligent electronics. Basically, what you can see here is the sensor in the form of a capsule. It gives a temperature compensator output in the sense that independent of the environmental temperature, it gives an output that is constant. Then it gives an RS485 serial output port. It has got a built-in transducer electronics datasheet. It uses miniaturization using 3D packaging, and its weight is only 100 grams. Now, this is basically the block diagram of that. It has got a pressure sensor and a temperature sensor, which is used for temperature compensation. It has got an analog to digital converter. It has got a built-in microcontroller, and it has got RS485 transceivers, which will pump the data out through a serial port. So this figure basically shows the stacking diagram of that sensor. And this is basically a graphic which illustrates the performance that we get out of the sensor. That is when the pressure is plotted against the temperature, we can see that in the case of an uncompensated sensor, the pressure goes on, the pressure readout goes on changing with respect to temperature. Whereas when we apply a compensation, what is shown by the violet line, it is essentially constant with respect to temperature. So this is what for the one advantage that we get out of smart sensor technology. That is basically we are able to do a temperature compensation in situ. Now, this is another example of an energy harvesting wireless sensor network, which we have used in one of our missions, recent missions. Some of you, if you might recollect, might have read that we are planning a mission called Gaganyaan, where the astronauts will be taken to space. And as a preparatory test for that, we had something called a pad abort test in one of the recent missions. There, basically, a capsule re-entered the Earth's atmosphere, and it was recovered back. So basically, this test is used to prove something called a pad abort. That is, in case the launch vehicle is developing a problem at the launch pad, then we need to take the astronauts to a safe place. So there is a system called pad abort system for that, and that was particularly tested in this experiment. And there we use this wireless sensor node. So this wireless instrumentation system was used inside the crew module of that in order to measure certain parameters in a wireless manner. So basically, what does this consist of? I will just show you the diagram. It consists of the wireless base station, which is labeled as WBS, and a set of wireless sensor nodes. So these wireless sensor nodes were communicating at a frequency of 2.4 gigahertz, which is quite similar to Zigbee frequency, if you may know that. And here it can be seen that the wireless sensor nodes, what is shown in blue color, basically acquires the data from the environment, and it sends the data over a wireless node to the wireless base station. So what are the advantages of this? Basically, data communication is done by wireless means. That is the advantage. And in a launch vehicle or in a spacecraft, when we do this, we are able to eliminate the wires. The wires constitute quite a lot of weight in the payload bay of the launch vehicle as well as in spacecrafts. And therefore, by eliminating wires, we are able to reduce a lot of harness weight. So that is the basic advantage of this wireless instrumentation technology when we adopt it in spacecrafts as well as in launch vehicle. Now, what is shown as the RF source here in red is basically a dummy RF source, which is used in order to harvest energy. That is basically the wireless sensor nodes are having built-in circuits which can work on this energy which is derived from this RF source. So what is the advantage again? We need not supply power. So basically we are able to eliminate the power cables also. So in such a scenario, the wireless sensor node, neither does it have a harnessing for data communication, nor does it have a harnessing for powering. So basically we are able to eliminate the wires to the sensor node completely. That is the advantage. And these are basically some details of the energy harvesting that we have adopted. And there are some calculations which goes along with that to show how the energy harvesting will depend upon, or the amount of time that it can work on harvested energy will depend upon the amount of activity. It's extensive characterization. That is the basic message that comes out of this. But anyway, what we can see here is that we have done the design, and we have flown it successfully also in the so-called pad abort test mission that I was talking about, which is a precursor to the Gaganyaan mission. That is the human in space mission that ISRO is planning shortly. So this was one work which we have done. And now that is basically an example of a case study. Now let us see what is Internet of Things. That is another topic which we are touching upon in this lecture. The Internet of Things is a scenario in which objects, animals, or people are provided with unique identifiers and the ability to automatically transfer data. So IoT has evolved from convergence of wireless technologies, micro electromechanical systems, internet, and smart computing techniques. So IoT is basically a convergence of these various technologies that we have touched upon here. So a wireless network between objects, usually the network will be wireless and self-configuring. These are some of the definitions of IoT. By embedding short-range mobile transceivers into a wide array of gadgets, which can communicate between people and things and between things themselves. Number of technologies lead to this, such as internet and the real world of internet incorporated into the real world of physical objects. Now, what are the components of IoT? Sensors, smart computing, people and processes, and connectivity. These are the various arms of this technology driving the IoT. So cheap sensors, cheap computing power in the cloud, big data, then concepts such as AI-based computing, advancement in VLSI, MEMS, and nanotechnology. All these technologies converge in order to make IoT possible. So what are the key technology elements of IoT? Tracing and localizing, that is tagging things. Sensors, that is feeling things. Wireless connectivity, that is linking things. Smart computing, that is things which can think. Then energy harvesting, that is powering things. Then smart packing and nanotechnologies, which is basically shrinking things. So this is what IoT encompasses in its technology. Now let us look at some of the very interesting applications of this. For example, biomedical application, where I want to know more about myself. Where are you going? For example, who you have interacted with. All these answers can be derived by using wearable devices, as we all might have read. Then, for example, questions such as how well do I sleep? Your sleep pattern can be logged by using a wearable device, and that will help the doctor to analyze whether you are having your health is okay. Then thought-controlled computing. These are just some paradigms which of new technologies. Then thought-controlled computing, that is basically something which can be done by invoking thought. So basically what it does is there will be a set of electrodes in order to capture the EEG or brain waves, and then it will there will be a computer to analyze your brain waves and then activate some of the actuators in order to do a certain action which you are thinking about. So that is something called thought control computing. Now just think about the power which this can give to, for example, a person who is handicapped. So this is, for example, a technology which is going to revolutionize the world of a person who is handicapped, as well as, for example, persons who are in coma. Even people who are in coma, they can benefit from this. So whatever thought they are having can be picked up by using electronics, and an action corresponding to that can be initiated. There is a lot of research going on around the world in these lines. Then glucose monitoring, for example, another typical application of even the COVID monitoring, as we know, is another application. So these are all biomedical applications. Now, a typical example of a wearable device, a self-powered wristwatch style health monitor. So this is again some news which has come from NASA medical briefs. It keeps track of wearer's pulse, wirelessly communicates to a nearby smartphone or tablet without needing an external power source. So how is this accomplished? It has got two modes of operation. The energy created by tapping the wristband is harvested by using nano energy generators, something called triboelectric nano generators, which works on mechanical thumbing. So it powers up the sensor circuitry, and soon the wearer's pulse rate will appear on the LED display. When a smartphone or similar device is held near the wearable, then it can communicate with the smartphone, and then we can get a plot of our biophysical information as well as pulse rate and all those kind of details on the smartphone screen. So this is a typical example of a wearable device which is able to communicate the parameters to a smartphone which is kept nearby, and it works without a battery. That is the major thing which we have to notice here by using triboelectric nano generators. So this is another example of an agricultural application where a hydroponic system is used in order to monitor plants and in order to see the plant's needs such as manure, water them, etc. Then a smart mirror, a reflective mirror with programmable applications and digital display for home, office, etc. is another example of an IoT device. So in conclusion, power is a distributed problem. It spans all disciplines, standard software, digital, etc. Right combination of silicon software and development tools is required. Design decisions must be weighed against all of the system constraints, like size, cost, performance, etc. Low power design techniques have to be implemented at different levels. New paradigms like advanced non-conventional VLSI, etc. will be required in order to achieve optimum power consumption. So what are the technologies that can be used? Advanced non-conventional VLSI, MEMS, nanotechnology, energy harvesting, green and smart embedded systems. Then these are all things which go into the smart electronics needed for IoT applications as well as aerospace. So these are some of the references. If there is any particular topic which you need to discuss, you can always feel free to contact me. And I will just now try to show one or two videos of some smart systems. So please allow me to play the video. So the first one that we are going to watch is basically a wireless sensor system which can detect leaks on International Space Station. So basically it is a wireless smart sensor system which can detect, which is used to detect gas leaks on International Space Station. So let us see. Are you able to see the video?
Not that, sir.
Okay.
Not at played, sir.
Are you able to see?
No, sir.
No. Still, PowerPoint is there.
Okay.
Possibly different screen has to be shared, different window has to be shared.
Window has to be shared.
Now it's okay?
Yes, yes. You can start from.
Okay, I will start from the beginning. Yeah. Okay, so that was about a wireless sensor system to detect leaks on the space station. Now let me see whether another video I am able to show. Are you able to see now?
Yes, sir.
Okay, so that was a news from MIT on a wearable device on your thumbnails. So basically, it was a wearable device which was mounted on thumbnail, and you are able to control many of the things by using that embedded system. So it is basically an example of a system which is packaged into a very small dimension with a very small power consumption also. So that is again a typical example of a smart system which helps us to do various kind of things without actually using even our hands. So with that, we come to the end of the talk. What I would like to tell is that any particular topic which seems interesting to you, you can always we can always have a conversation, and I will be happy to share whatever literature I'm having on that. Okay, so thank you. Any questions?
So participants, it's open for you. Anybody, if you want to ask any question, you can unmute your mic and you can ask directly.
We see a question here. Do the junction capacitance? I'm not able to read it out.
Sir, I will read it.
Yeah.
Do the junction capacitance will affect the overall performance of the system as we go for miniaturization in low power design?
Yeah. Junction capacitance is one of the major contributors towards the parasitic capacitance. For example, when we design the we're using the MOS technology, and when we do the MOSFET, the particular MOSFETs that we are using, one of the important things is the parasitic capacitance. The parasitic capacitance, when we tell what we mean, is the gate to source capacitance and the gate to drain capacitance. And the junction capacitance is also a very important constituent of this parasitic capacitance. And an increase in junction capacitance leads to slowdown of the circuits. So it definitely is one particular factor which has to be optimized. And when they come up with new technology generations, they always assess what is the effect of this gate to source capacitance, gate to drain capacitance, as well as the junction capacitance on the circuit operation. So that is one of the things which is always studied well before the circuit design takes place. Can we design any compensation network to solve this problem? But basically, when we are thinking about the parasitic capacitance, as you told, some compensation networks may be possible, but it adds to the circuit complexity. So there is nothing like optimizing the MOSFET structure itself in order to reduce the gate to source and gate to drain capacitance as well as the junction capacitance. But circuit techniques may be there which will add to the circuit complexity and probably add some power dissipation also. So whether it can be done in a non-invasive way is to be seen. That has to be seen. Yeah.
Hello, sir.
Yeah.
I'm myself Daya, sir.
Yeah.
So first of all, thank you, sir. I'm very late to join this session.
Okay.
But anyway, having very interesting topics, sir. You are delivering all things are very good, sir. Very new for me also. Maybe wonderful session, sir. Thank you. And most last videos are very clippings are very nice, sir. Because of the I'm not aware of the side also for the piezoelectric sides.
Yeah.
Maybe the timeline is very interesting to share this thing, this kind of things. I'm not asking any kind of yeah. So I'm keep moving on, always searching for the electronic side, what's on new. But I'm in very low side from your session. Really, I'm thinking about myself. Keep going on, improve myself. Thank you, sir.
Okay.
Thank you for wonderful sessions.
Yeah.
Thank you.
So one question is there: how the IoT devices and big data connected?
Okay, basically the thing is that when this IoT comes about, and you are able to produce all these things in a very small form factor, and therefore you are able to do a lot of monitoring. Like for example, for example, let us take the example of a bridge. For example, if you want to see the stability of the structure, then you can instrument it heavily. So when you are having this power of producing very small smart sensors, which can work with batteries or which can work for prolonged periods of time, then you get the capability to monitor quite a lot of things. For example, environmental monitoring, the study of atmosphere, the greenhouse gases, and prediction of weather. For example, there are this technology will allow us to install weather stations even in remote places. That is an example of what this allows us. So basically, the thing is that when we are having all these kind of monitorings, then the amount of data goes up, right? So the amount of data that we are going to get is going to increase exponentially. So there comes the importance of big data. So how do we analyze this data? How do we make sense out of this data? And how do we derive some information out of this? So all these become very important. So this is especially important in the case of big systems. Like an example of a big system which I can tell you is, for example, our launch vehicles. Because I am directly associated with it. Launch vehicles such as GSLV Mark III, which is our biggest launch vehicle till date, Do you know how many parameters are monitored there? About 2,500 parameters are monitored in that launch vehicle in each flight. So when you are having the power to produce these sensors and this data acquisition systems in a very small form factor with low power, then you get the power to monitor more of this, and therefore you get more amount of data also. So similar is the case with or concepts like smart cities, etc., where you are having a lot of monitoring. So big data comes in there, and then you have got all the associated techniques in order to analyze that data, store that data, derive meaning out of that data, and derive some conclusions out of that data. So all these become more complicated. So that is where big data comes in along with IoT. And that is the relationship between the two. Okay.
Sir,
yeah.
One question. What about the role of transients as we consider the analog case, especially in small signal analysis?
Yeah, that has to be analyzed anyway. The transient analysis is one of the important analysis that you have carried out, that you have to carry out in the case of analog circuits. So that has to be done. So do you mean that it is complicated? Like, but there are tools to handle that now. So even for mixed signal design, where both analog and digital comes in also, there are number of tools that can handle all these transient situations. But basically will it affect the power consumption? Yes, surely it is going to affect the power consumption, because analog, as you have rightly pointed out, works with some transient phenomena. So it is going to affect the power consumption, but there are techniques even to optimize this power consumption also. Like, for example, similar to that digitally assisted analog that we have seen, even the implementation of analog circuits itself are carried out nowadays by using techniques such as switched capacitor techniques. So they are techniques which can lead to a reduction in power, even if transient conditions are there. So those are typical examples of how digitally inspired analog design can be carried out. Okay. Then another example which I can tell you is, for example, the sigma delta ADCs. So that is one category of ADC which taps the digital advantages of digital circuits very heavily. So, but they are basically nowadays used, very popular and used in a large number of data acquisition applications. So these are some of the examples where we derive benefit out of analog, derive benefit out of digital techniques in order to aid analog design. Okay.
Hello, sir. Good evening.
Yeah.
So my name is Soumya. I'm from Digital University, Kerala. Sir, I would like to know about one topic related to memristor, sir. Memristor. So since we are implementing the memristor in analog circuit, can we replace that memristor with our? Can we replace resistance with the memristor?
Yeah, basically it is, I think, but the thing which you have to consider is a resistor is a simple element. Application will require some specific materials, right? For example, some nanotechnology or nanomaterials may be sometimes required. So the fabrication of memristor, whether it has come to a mainstream commercial, this one, and that has to be seen. So, but otherwise, if it can be produced in a mass scale batch fabrication techniques at low cost, then definitely memristor can be used as a replacement for resistors. Probably a versatile replacement, right? That is what you mean.
Yes,
because
sir.
when you get, we get more power out of memristors. So that is possible. But the only thing for any technology to be successful, this is what possibly you all students also have to be aware of. For any technology to be successful, it must be possible to produce it at low cost in batch fabrication, like especially if it is required in large numbers, it should be possible to produce it at a low cost in using batch fabrication. So why are we all able to use mobile phones now? Because the mobile phone can be fabricated by using batch fabrication techniques, and it is not very costly. A smartphone can be the cost is around something like 5,000 rupees. You are able to get a smartphone. So if such a thing is not possible, then how many of us will be able to use smartphones? So that is one of the major things. Even though technology advancement takes place by introducing new device, etc., if they have to come to the mainstream of commercial production or industrial use, then it should be possible to produce that in large numbers using batch fabrication techniques at low cost. That is one of the successes of the IC technology also. So I am not telling that memristors won't come into mainstream, but it may take time. It may take some good effort also. But as when they come, they can replace resistors. There will be a versatile replacement for resistors.
So similarly, can we replace a potentiometer instead of a memristor? Sorry, memristor can be, a potentiometer can be replaced.
Right, surely. Nowadays, there are even potentiometers which can be digitally controlled. I don't know
digital
whether you are
potentiometers.
aware.
Yes,
digital potentiometers are there which don't require mechanical tuning. By the way, we use back in VSSC, we use a lot of digital potentiometers to do something called balancing of our strain gauges. We are having a lot of strain measurements there. In order to balance the strain gauges or eliminate the offset out of strain gauge, we use these digital potentiometers in a electronically controlled fashion. So that gives us the power to control the potentiometer in a digital software controlled manner. So definitely once memristors come in the mainstream, they can be used for, we can think about a lot of versatile applications for those devices.
Okay, thank you, sir.
Yeah, thank you.
So I think no more questions are there. So we'll wind up. So sir, it was a really wonderful session. Started off with the concept of power and energy in low power design. Importance of low power design and its different techniques, both in hardware and software aspects were talked about, and discussed about the new hot topics of era like green electronics, smart electronics, and bio-inspired electronics. And finally, to conclude with, to have a real insight on the topic, a case study and its application in IoT, biomedical area, and agriculture was discussed. So really, it was an excellent talk. Hope all the participants might have gathered many information from the talk. On behalf of IEEE Malabar Subsection, IEEE Solid State Circuit Society Chapter, IEEE Circuits and System Chapter, and IEEE Educational Society, I would like to thank the speaker, Dr. Sreelal Sir, for sparing a 1 hour with us and having a wonderful interactive section on the topic, low power smart electronics for IoT and aerospace application. Thank you, sir.
Okay, thank you, Sabik sir and Kasim sir, also the SSCS office bearers, CAS office bearers, for giving me this opportunity to reach out to some students, because we don't generally get this kind of opportunity when we work back in ISRO. So it has been a wonderful opportunity to interact with the students also. So thank you for that. Okay.
Thank you, sir.
Okay.
Next, I would like to thank all the participants who have taken their valuable time in attending this section. A feedback link has been shared in the chat box for sharing your thoughts and suggestions and feedback. And this is also used for availing your participation certificate. Thank you once again. And with that, we wind up this session. Thank you, sir.
Thank you, sir.
Yeah, thank you all. Thank you, Sreelal sir, and thank you all the participants once again.
Okay. Thank you,
From our part, Kerala section part. Yeah. Thank you.
Thank you.
Good night also.
Good night.